Alright, let's start today. I'm gonna put the timer here. Palindromic substrings. Given a string S, return the number of palindromic substrings in it. A string is a palindrome when it reads the same backwardness forward. A substring is a contiguous sequence of characters within the string. Number of palindromic substrings. Okay, so I have to return all of them. Yeah, that sounds really hard. It feels like it should be a hard problem, given the amount of accepted and submissions, but so the first thing that I think about is using a dictionary to keep track of the frequencies of words. I seen this a similar problem before or yesterday when I was watching the Midnight Simon stream, and on that one I think he solved using a hash, keeping track of the frequencies and checking the values later. But here it may not be possible because I have to find all the substrings. And I remember for the other one, the first thing that came in my mind was using a sliding window technique, but I'm not sure how to do it because it's hard to know what's gonna be the end of the window. You could put something like the end of the window being the same letter as the first one, but then it obviously fails in a bunch of situations because you have words that have the same letter in between the word or the sentence. So the other approach you can think of is using creating another function for finding the palindromes and then applying this function at some portions of the string. And maybe that's what they want you to do. I wonder if you can use a try to find palindromes as well. You probably can. This is definitely related. Oh, maybe a palindrome is a cycle in a try. It's also an interesting idea, actually. But it might not be because tries are for adding words, but yeah, I don't think you can really add sentences in tries because then you would change the structure as a whole. So how can I do this? Let me think. Oh, I should probably take off the camera as well from the stream. Yeah, there we go. Yeah, I have no idea how to do this. It's really hard to think about a way to create a heuristic to find a palindrome inside of the string. Maybe I can combine these two techniques, but I know it's a dynamic programming problem. But I don't really understand what dynamic programming is yet. I think it involves memorization. So maybe I should find words. 4 divided by 2. Then left or right equals 0 for letter word or right left in range 4. Or right should be length word. I think that's the algorithm to find the palindrome. So maybe now I can implement this sliding window on the first one and apply this function for the sliding window. So I can say while that find pal passing the substring. But then how? Yeah, I need to create two pointers in the first string, I think, for the sliding window, and then somehow we need to probably apply memorization as well. So probably create a set and then pass. Each time I find a palindrome, add it to the set, so I don't have repeating ones. But then the issue is I'm not sure if the set's gonna be. I'm not sure. It's probably better to use a hash actually, because I think the set is not good. It's gonna remove the repeated letters. If I pass the strings, then it's not gonna be able to check if it's the same or not. So it's probably better to use a hash. And then each time I find one, I pass to the hash. I don't remember really well how to solve sliding window problems. I think you do for I in range length pass. You move one cursor and then based on a certain condition you move another one. And the biggest challenge is what defines words here. Maybe I can do list here or stack. Let's just call it stack. And then I do while. Oh, but I have to accumulate. That's the issue. And the problem here is that I need to call the function on the while thing. But I can't increase the size of the letter. That's the problem. Or maybe I can actually. Oh, but then I'm gonna break out of the loop. Or maybe not actually. If I do currents is plus equals si. And then ball. So we should find ball with currents. Ball. Yeah, maybe this works actually. But I need a way to increase the size of the letter inside of the loop actually. Yeah, I don't think this way that I'm trying to do is actually good. Because first I would have any single letter is going to be a palindrome, so I would have to push that into the set. But then I would have to keep the loop going and also I would have to keep calling the function. So maybe it's a recursive approach is better, actually, now that I think about it. Because like I can pass the word and call it recursively. Huh. This might be an interesting approach, actually. Yeah, but then I would have to figure out how to decrease the size of the string on each recursive call, which is quite annoying to do. I can create a for loop inside of the function and then base the increase or decrease the size of the variable in the for loop to decrease the size of the string that I'm to get the substring from the main one, but I also have the feeling that is not the best approach. Substring stack. Huh. So what else can I do? So here I'm thinking find the other thing I would have to make at some point I would have to make current equals empty string again. So I initialize here, and maybe I have to initialize at outside of the loop so that the sum works here. So I would add a letter and then I'll do this, call the function, and it's gonna give me true because it's a single letter. And then I append that maybe to the set or to the stack. Not to the stack, to the all all polling currents equals currents equals currents. And then after that, I increase the size of the other cursor. Maybe this works actually. Because, yeah, here I do a recursive call. They're not really recursive, but... So maybe here all I have to do is make it equal because I'm going to increase here. I plus equals 1. Find all currents. But then the issue is that I think I'm not going to be changing this value here because there are different things. Alright, maybe I can do just like this then. And then here it would have to be outside of the loop. So let me think. So I'm creating this variable to create a different string each time, call in the pol, then pass here, and then here at the end, I would... So this is going to return true or false, so I would have to do this again. Because it's going to be two different currents. One is going to be the first letter that I started the loop at, and the other... Yeah, but the issue is that the palindrome is not necessarily going to be... I have to start at the end, that's the issue. So I think this method doesn't work. Because you can ABA, for example, and it is a palindrome, but and the second letter is not going to be the palindrome. So this sliding window has to be with 2 pointers. That's probably the reason why it doesn't work. I suspect that I think there's gonna be a hash in the solution. There's gonna be the other ones I'm not really sure, but I think there's gonna be a hash and a recursive call. But from the other that dynamic programming problems I saw, he used a for loop, so not really sure. Yeah, I think I'm gonna look at the solution.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve palindromic substrings. And this is another problem from the LeetCode blind 75 list, a list of 75 very good LeetCode problems to solve. And this time we will be doing palindromic substrings down here. And so we are getting one step closer to filling out this entire list. And this problem, palindromic substrings, is actually really similar to another problem I've solved, longest palindromic substring. So if you would like to, I'd recommend watching this video as well, longest palindromic substring. I will probably link it in the description below. So simply, we are given a string S, and we just want to return the total number of palindromic substrings contained in the string S. And as you may know, a palindromic substring is basically a string that can be read backwards, and it's the same string. So, A, if you read it backwards, it's the exact same string, right? A, B, A, this is the same string reversed. Because the first character is the same as the last character, and then in the middle, we're just left with one character, and, basically that kind of pushes us towards a base case. So as you may know, there's two types of palindromic substrings, strings of odd length, right? So for example, just a single letter A, that's a palindrome, right? It's the same backwards. If we add a B to the beginning and a B to the end, it's still a palindrome because now we expanded it outwards with the exact same character. Similarly, we can do the same thing with even length substrings as well. If we have two A's in the middle, then of course this is a palindrome, and then if we continue to expand outwards, we add a B at the beginning and we add a B at the end, it's continuously going to be a palindrome because these characters are also matching. Now if we, instead of adding a B, we added a C at the end, the inside is a palindrome, this string of length 2, but now if we expand outwards, this is not a palindrome, right? Yeah, it can't be read backwards. C is not the same as B, it's not a palindrome. So that's a little bit about palindromes, even and odd length. But so how can we apply that to our input? So in this case, we are given a string A, B, C. Now, of course, we have three different palindromes because each character by itself is a substring, of course, and each of those by themselves is a palindrome as well. So that's three. Now, is any other substring, for example, AB, that's not a palindrome. BC, that's not a palindrome. ABC, that's also not a palindrome. That's basically all the substrings available to us. So we only find three, so we're going to return three. So let's understand how we can do the brute force solution, which is actually big O of n cubed, and then we can actually optimize it a little bit, understanding how even and odd palindromes work, and then we can get a big O of n squared time complexity solution. So let's say we're given a string that looks like this. If we just start brute forcing it, we want to go through every single substring, right? So every single substring starting at this first position would be something like this, right? There's these substrings, right? Then we want to go through every single substring starting at this position, which would look something like this, right? In total, there's going to be n squared substrings, right? And for each substring, for example, this one, we need to determine if it's a palindrome or not. And we know, that's not a difficult algorithm to write. We can have two pointers, one at the beginning, one at the end. We basically keep comparing the characters and making sure that they're the same, right? So, and for a substring like this, we'd also have two pointers, right? Compare that, okay, these two characters are the same, so then we can move inward, right? We'd shift our pointers here, and then we'd see, okay, this character is also the same, and then, we go through every character, so we determine, yes, that's a palindrome. Then we can increment our count of palindromes, right? We'll call that our result variable. So then we'll add one to it, right? Because that's ultimately what we're trying to return, the number of palindromic substrings inside of this string S. And clearly finding and determining that a string is a palindrome is also big O of n. So since there are n squared substrings in the entire string S, and for each of those substrings, we have to determine that it's a palindrome, we're going to multiply it by n, so this is going to give us an n cubed time complexity. Now, we can improve this, and it's going to require us to solve this problem in a different order. What we're instead going to do is we're going to go through every single position in this, right? Instead of finding for this position all the substrings that start at this position, we're going to find all the substrings that this position is the middle of. So instead of, just going to the right, we're actually going to expand in both directions. We're going to go through all substrings where this position is the middle position. Now, clearly, this string itself is one string, right? And this is a palindrome, so we're going to have our left and right pointer just initially at this position. We're going to see that, okay, both of these characters are the same, right? So then we can take our result, add one to it, right? So we did find one palindromic substring, and then we're going to try to expand outward, right? Our left pointer is going to go here, our right pointer is going to go here. Clearly,
That's actually really smart. That's what I was thinking about, is that the biggest issue there is that if you start from the beginning, you stop. Just like I was saying, if you pass the two other words, if you have ABA, then it's not going to be a palindrome. So starting from the middle, I didn't realize that as I was thinking. I was thinking more either starting from the beginning or to create the 2 pointers. And I guess it's just because when you're working with loops, I have no idea how I was going to do it from the middle. But it's not the first thing that you should think about, because it's probably harder with the pointers to figure out a way to start in the middle. That's why I didn't think about that. It was really interesting.
Clearly, we go out of bounds, though, to the left, right? So basically what we're saying is there's only one substring where this is the middle position of. And then we're going to do the same thing for here. So from this position, we want all substrings where this is the middle of. So we're going to have our left and right pointer initially here. Yes, this character, our left and right pointer point at the same character. So we found one palindromic substring, just the single character itself. Then we're going to take our left and right pointers and then shift them. So left is going to go over here, right is going to go over here, right? So now let's compare left character and right character. Since we already know this middle portion is a palindrome, right? Now we only have to compare the left and right characters, the new left and right characters, if they are equal, right? Which they are, A equals A, right? So therefore, we found one additional palindrome, this palindrome of length 3, where this character is still the middle position, right? So now we found an additional palindrome. So I think our total number of palindromes is up to 3 now. And once again, we're going to take our left pointer, shift it to the left, right pointer, shift it to the right. Now clearly, once again, our left pointer goes out of bounds. So this is, we can't really find any more substrings where this is the middle position. But do you notice how what we just did, right? We cut down on repeated work. We found that this is a substring, and then in another single operation, we found that this is a palindromic substring as well. That cuts down on the repeated work. Whereas before, we would have done something like, okay, this is a palindromic substring, then we increase it, then we have to look.
So I think it's going to apply a similar thing to the binary search logic, or yeah, I think it's binary search name, where you split the array into 2 based on the middle. But he's going to start from the middle using the half of the length. And then he's probably going to create a function to find the palindrome like I did and create 2 pointers that both start at the middle, but one decreases and the other one increases. And then he's going to loop through the first one, through the main one, to the beginning, and apply those 2 pointers for each character calling the function. But I think it's going to be probably O(n) square, if I had to guess.
Look at both of these, and if we continue to increase it, if we go all the way here, then we have to still check, okay, this is the same, and now this is the same, right? We're continuing to do repeated work. If we start from the left and then expand to the right, but if we start in the middle and expand left and right, then we eliminate repeated work. So let's do the same thing from here. So this is a palindromic substring, right? Left and right point at the same character. Then we expand once to the left, once to the right. Are these characters the same, right? Are A and B the same? They're not the same. So we knew that the initial substring just in the middle over here, the single character was a palindrome, but when we add this character and this character, it's no longer a palindrome. This is not a palindrome. So no matter what we do now, if I expand one more to the left and expand one more to the right, even if these characters were the same, assume we had an A in both positions, it doesn't matter because the subproblem, the substring in the middle is not a palindrome, so therefore no more substrings expanded from the middle of this position to the left and right. None of those additional substrings are going to be palindromes. So far our count of palindromes is at 4, I believe. So now let's go to the last position. So we want to expand from this middle position. So we're going to go, so initially we're going to say, okay, this itself is a palindrome, so we can change our count of palindromes to 5. We try to expand left and we try to expand right, but again, we go out of bounds to the right side, so we're done. So in total, we found 5 different palindromes, but it turns out we actually missed a couple. We missed this palindrome of length 2, and we missed this palindrome of length 2. How is it that we missed palindromes, and how is it that they're both length 2? Notice how we were starting at each middle position, so this was a length of 1, right? As we add the adjacent positions, then we're increasing the palindrome to length 3, and then if we added a couple more, we'd increase it to length 5. So we're only getting palindromes of odd length. If we want to get palindromes of even length, we have to start at every single even position. So we'd have to start at here, and then this is a substring of length 2, then we'd expand by 1 more, so then we'd get palindrome of length 4, and et cetera, just keep increasing it by 2. So this is how we're going to get palindromes of even length. So when we do this, we're going to have our left pointer initialized here, and in this case, the right pointer is actually just going to be left plus 1. Before we were doing it as left and right both starting at the same position. In this case, right is going to be left plus 1. And so in this case, we see these characters are equal, therefore they are palindromes. So we can increase our count from 5 to 6. We expand outwards, left and right, but we see left is going to be out of bounds, so then we can stop. So next, we're going to basically do the same thing for every pair of adjacent characters, right, to find even length palindromes. So here, left and right are once again the same, so we're going to get our total to be 7. When we expand to the left and right, we see we have an A and we have a B. These characters are not the same, so we can't continue to expand, and we don't increment our result. So now we have 7 palindromes. This is the last even length substring that we're going to start at, and the left and right characters are clearly not the same, so we don't continue to expand, and we don't increment our result. So we're done with everything here. We get a result of 7, and the overall time complexity of doing it like this, it's going to be big O of n, because for, let's say, the odd lengths palindromes, we're starting at every single position and potentially expanding outwards all the way to the end of the string, so that's going to be an n time operation. So since we're doing it for every single character in the array, it's going to be big O n times n, right? So that's basically how we're doing the odd length palindromes, and the same time complexity is going to be true for even length, right? We're basically going through every pair of characters, which there are, big O of n of them, and then we're still expanding outwards, so that's also going to be big O of n times n. Now, if you add these together, we're still going to get a overall time complexity of big O n squared. So that's the overall time complexity in this solution, and coding it up is pretty easy, so let's get into that. So let's keep track of a single result variable, and it's initially going to be 0. It's going to be the count of the palindromic substrings. So we want to go through every single position in the string S and expand from it, right? That's going to give us the odd length palindromes. So we're going to initialize our left and right pointers both to be set to I, because these are odd length palindromes, and while left is inbound, so while left is greater than or equal to 0, and right is inbound, so right is less than the length of the string, and the position at left in our string is equal to the position at right in our string, that means we found a palindrome. So let's increment our result by 1. Let's shift our left pointer to the left, and let's shift our right pointer to the right. And we're going to continue to do that while the pointers are inbounds and the characters are the same. Then we're going to continue to increment the number of palindromes. So that's going to give us the palindromes of odd length. We don't have to do a separate for loop for the even length palindromes. Let's just do the exact same thing we've done up above here, except in this case, we're going to initialize left to be I, which is what we did before, but we're going to initialize right to be I plus 1, which is going to give us the even length palindromes. And once we've done that, we can literally just copy and paste this for loop up above down here, and then that'll calculate the even length palindromes, and then once that is done, we can go ahead and return our result. Now, as you can see, this solution works. That's the entire thing. It's very efficient, but maybe your interviewer will want you to, this is copy and paste, and sometimes they don't like copy and paste. We can basically take these two and condense them down into a single function. So I'm just going to do that, even though I'm sure you could probably figure out how to do it. In this case, it's not too bad. So I'm going to make a function called count palindromes, and we'll pass into this the string S and the left and right pointers that we are initializing. And so basically what I'm going to do here is take this and just copy and paste it into here, right? And so you can see that we're giving this function the information it needs. We're giving it the string S, we're giving it pointers left and right. Let's just give it a variable here. Let's declare it result is initially going to be 0, and then this function is just going to return result, which is the number of palindromes it can count starting at these left and right pointers. So now we can change this. So here we were trying to count the odd length palindrome. So instead of doing this for loop, we can just say let's add to the result the whatever this function returns. So count pally.
Yeah, so that's actually a lot better than what I did as well, is that he didn't even need to create, because it's so simple to figure out from. It's basically great. It's because the logic that he's implemented is different. I was thinking about separating the function to find the palindrome and this one, but he does in the same one, and it's a lot more efficient. And so I think I was kind of on the right track. It's just this idea of putting the 2 pointers at the beginning of the palindrome, at the middle of the palindrome, didn't occur to me. But it was pretty much the same thing I was thinking. And that's the reason why I was thinking the sliding window technique, because you have to find the substring inside of the string. But this way is obviously a lot better.
Passing in the string s, passing in the left pointer, and passing in the right pointer, which we just declared up above here, and getting rid of this while loop, we can do the same thing. So add to result, whatever this function returns, count pally, passing in s, passing in left, and passing in right. And if we really want, we can take left and replace it with I, and right and replace it with I plus 1, so then we can get rid of these two lines. And up above do the same thing, so replace left and right with both I, and then get rid of this line. So this is a pretty condensed version of this function, so with this little helper function that we have, we can cut down on that repeated code that we were writing and basically get the same result, same efficiency, same everything.
Cool, let's go to the next one. Start a timer. A message containing letters from A to Z can be encoded into numbers using the following mapping. To decode and encode a message, all the digits must be grouped, then mapped back into letters, using the reverse of the mapping above. There may be multiple ways. All the digits must be grouped, then mapped back into letters. Okay, I think I understand. For example, yeah, but it doesn't seem... well, because every number... well, but if you have 1 and 11, how are you gonna know? And I also don't understand. So 1, 1, 10. And 6. I guess it makes sense. Because you can't have... or maybe you can have... can't have 100. But you can have 11, and then 1, and then 0. Well, don't have 0. That's why. Grouping... oh, so it can be mapped into two different things. That was what I was thinking about. Note that the grouping is invalid because 0, 6 cannot be mapped into F since 6 is different from 0, 6. Given the string S containing only digits, return the number of ways to decode it. The test cases are generated so that the answer fits in a 32-bit integer. Let me think. Now this sounds really hard. So the input is a string of digits. And then I need to figure out how to... the number of ways that it can be. So I think what's going to increase the number of ways is repeating characters. Probably. Yeah, but this one I'm having trouble with the logic, which is not usual for me. Usually I know the logic, or I can think about the logic pretty quickly. When I struggle with the programming part, translating the logic into something that works and is efficient in programming. But in this case, I'm stuck at the logic, I think. It's kind of hard to think about how to organize this, given all the possible different ways that the string can be organized. Maybe I can, yeah. There's also the issue with the 0, because if I split by the 0, then There are some that are gonna have, and some strings that are not gonna have. So what's the similarity between? I think the reason he put this question right after the other one is because it seems really similar to the previous one. I think I can probably apply the same pattern he did on the last one in this one somehow. So remember he did for I in range length as. Then you have a different function. It's called find. Then left, right. Yes, I don't remember really well the third argument. One has to be soft here as well. Soft dot find I soft dot find I plus 1. And then I think the logic of the function is here. While left is greater or than 0. And right lower than length as and as now go to as right and left plus equals 1 right is equals 1. And then I should probably have a list here to append the letters, the current letter. So this is for the even palindromes. This is for the not even. No, this is for the odds, and this is for the evens. So this is the bounds of the string, and check if they're equal. But it's not the same logic on this one. So I think it's the same structure. It's just a different condition here to upgrade the pointers. So maybe I can do if left equals 0. If s left equals 0. And then I stop. So it has to be different than 0 because there are no leading zeros. And the tricky thing is how I'm gonna capture 1 and 11. Because if I put a condition to stop at 1, then I'm not catching 11, and vice versa. Maybe what I can do is find the minimum number that exists on the mapping and separate the original string into those minimal numbers. And then later on check to see if I can combine them in different ways to form the other one. To form other numbers that exist. But it feels that it's probably not the best way to go. Can have true one. And what else can I try here? So I think the cap is true. So a number can only be represented because it's 2 digits, obviously. So a number can only be represented between 1. I think that's the better way to think about it. Every number can be represented either with 1 digit or true. So maybe I should check if a number can be represented with 2 digits. And I can... Yeah, I can pass here. I can create this function for only 1 digit and separate the string. Yeah, that's a good idea. Another thing that I'm not really sure, I think they don't pass the mapping, so I probably have to do the mapping myself, which is quite annoying. But I can do something like this. Oh, map. Obviously, it's gonna make it slower, but I don't really care. Just about now I wonder if I can use, if I should use the indexes. I would just make it like this. So all map is gonna be the mapping of all the letters to their respective number. And then what I can do is, no, but the problem is you can have mix between 1 and 2 characters as well. So maybe that's where the dynamic programming comes in, I think. It's because you have these branches of decision trees. So it can be viewed as a decision tree, where at each point you can have 1 or 2 characters. And then you're probably gonna memorize in order to decrease the size of the tree. So the tree is only gonna contain unique decision points, I think. And the other ones are gonna be reused. But I have trouble thinking about building the tree itself. Even though I understand the structure. So that's the stuff I have to work on. I think scratch this idea. Oh, the functions there. How can I make that decision tree? So maybe because it's gonna be unique, it has to be a set. Tree. Oh, it has to be digits as well, I forgot. Hmm. So the mapping should be the letter, from the digits to the letters. I wonder if I can do this as well. And maybe it will have to be another dict or dict. So I can initialize like this. Then if I, if si in our map, yeah, but the biggest problem, so not in our map, in tree, not in tree. Or maybe it's better to create a tree first. So I need to have something that has all the possible combinations of digits from 1 to 26 in a string. That way I can use the loop to navigate to the, or maybe the set itself is gonna be, oh actually, yeah, you use the set, the tree, and for all the possible combinations to navigate through the original string, I think. And you return that, the path in the set. Hmm. So the thing that I'm having difficulty with here is thinking about how to build the tree from scratch. And how I'm gonna add, because for each breaking point in the decision tree, so maybe it has to be an object because trees are nested objects. So instead of a set, I make an object. But then I want to have to create a different class, I think. And I suspect that it's probably not the solution that he's gonna give. But I think the way that you could do it is create just like the standard tree where you create a node for each decision and then we make a left and right value and then you loop through the numbers and for each number you create a left and right based on the digits. But then I still can think about a way to get all the possible combinations, to write the logic so I can get all the possible combinations in that. Because it's not gonna be just repeating characters, or you have 1 and 11, for example. You can also have 12, so how you're gonna go from 1 to 11 and to 12 and 13 and so forth. So you can have, how are you gonna write that down into an algorithm? Maybe you can have for every letter in from 1 to 9 you loop through 10 and create the branches like that. Yeah, each level has from 0 to 9. So the first level is 0 to 9, then the other one is the combination of the from 1 to all the other ones. Maybe that's the way to do it, actually. And then what is the root of that tree? And then depending on how many decimals you have, a different level. So only 2 is gonna have the level below. So it's gonna be from 0 to 9, then the 2 is gonna have from 2 all the way to the... Oh, actually, no. It's only the 1 and the 2 that have the other level. Yeah. And the only thing that I can think about is what would be a good root to put there in the beginning. Maybe 0, but I don't know if that makes sense. Probably not. So we'll look at the solution.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem decode ways. So we're basically given a string of integers, and we want to know, with that string of integers, how many different ways can we take that string of integers and decode it into a string of characters. And we're given a specific mapping, so we have 26 characters, and each integer maps to a different character. So we have an integer 1, 2, all the way to 26, and each of these integers maps to a different character. Now we don't actually need to build that string that we are mapping to, we just have to count the number of different ways we can decode it. So down here in the example, you can see a string like 12 can be decoded in 2 different ways. One way to decode it is just 1 and 2, because 1 maps to A, 2 maps to B. So that's one string, but remember, we can have double-digit values, so 12 actually maps to its own character. 12 itself maps to 11. So there are 2 different ways that this string of integers could be mapped to a string of characters, so we return 2 in the output. Now, as you can see, it would be very simple if we just had numbers 1 through 9 that map to characters, right? The problem comes from double digits, right? From 10. 10, a string like this can be taken in 2 different ways, right? 1, 0, or just 10, right? So that's where the complexity is going to come from. From a string like this, we could have 2 different decisions, so we're going to be using a decision tree to kind of figure out all the possibilities with this. At least that's going to be the brute force approach. The only problem is that there's going to be a few different edge cases we have to worry about. For example, we could have a string like this. We could have a string like 0, 6, right? What exactly does this map to? Well, 0 is not even in our input, right? Basically, 0 itself does not map to any character, right? 6 could map to a character, but 0 does not. So if we ever get a 0, a string starting with 0, that's invalid. So we have to return 0. In that case, this cannot be mapped to any, this cannot be decoded in any.
I think I kind of get it now. Dynamic programming is pretty much the same as a tree data structure. The only difference is on the tree you put values to sort a list or something like that, and dynamic programming you put the decisions you're gonna... But it's pretty much the same logic from tree problems, I think.
Anyway, so we return 0.
For the most
let's
part.
try to figure out the brute force approach to solving this problem, and in doing that, we'll try to figure out some of the edge cases that we're going to have to deal with. Suppose we have a string like this, 1, 2, 1. How many different ways can this be decoded? Well, let's say we start at the beginning, right? We could take 1 by itself, right? That's going to be some character, right? We don't really care what it is, but it's going to be some character. Now, we could also take the first 2 characters by themselves, 12 by itself, right? Because that's valid, right? So that's another decision. Starting from here, we could take 1 or we could take 12. And by the way, if this was a 0, we definitely could not take it. Then we'd have to just stop immediately, right? Because we can't start with a string starting at 0. But if we had something like 1, 0, right? A 10 maybe, then we can take it because it's okay if a 0 comes after a 1. And so basically any integer by itself, right? 1, 2, 3, 4, 5, any integer by itself except for 0 can be taken, right? So basically we can create any string of one number from 1 through 9 except 0, right? We're just not including 0. It cannot be taken by itself. Any from 1 through 9 are okay, right? So what we're going to see here is, okay, if we went down this path where we chose a 1, then the next character we're going to be at is the 2, right? Of course, 2 can be taken by itself, right? Any number except for 0 can be taken by itself. It can be decoded in that way. So when we're at this 1, or when we're at this position, we can take 2 by itself, or we can take 21, right? 21 is also some character. I don't know what it is, but remember, we had values from 1 through 26, right? So having a 21 is completely fine. That will decode to its own character, right? Now, of course, if we had something like a 27 over here, then we could not go down this path, right? Then we just would not go down this path because 27 does not map to any character, right? So we're kind of learning that, anything, the integers have to be within 1 through 26, right? And this 27 is not. Okay, and so down this path, we reached the end, right? We had a 1 and we had a 21, right? So there's no more characters to choose from here. So basically, this was one way that we could decode this input. So when we reach the end, we were going to count that as a 1, right? That means we found a single way to decode this input. So this was a good base case where we return 1. And from here, let's continue this one. So we left off at 2, then we get to 1. Can 1 be taken by itself? Of course, again, it's not a 0, so we can take it by itself. And so then we reach the end of the string again. So this is another good base case. 1, 2, 1 is a valid way to decode this string. So if we started with 1, over here, we could decode this in 2 different ways. If we start with 12, how many ways can we decode it? Well, if we start with 12, then we just have one character left, the 1 character. So that can be decoded another way. So this is another good base case. So basically, we saw that we have 3 different ways that we can decode this string. Now, just to kind of add a couple values to the string, what if we had something like 31 after it? So then, let's say we left off over here, we can choose the 3 by itself, right? Because any character except for 0 can be taken by itself. Could we take 31? We could not, right? The same reason we can't take 27. We can't take 31 because it's greater than 26, right? How are we going to determine that in the code? You can do it a lot of different ways. What I'm just going to say is we can only take double-digit values if the first digit starts with a 1, because if it starts with a 1, then for the second digit, we can take anything from 0 to 9, right? Anything from 0 to 9, because then, this double-digit value will either be between 10 to 19, right? And this value is less than 26, so that's perfectly fine. But if we start with a 2-digit, then the second digit has to be between 0 and 6, because 26 is going to be less than or equal to 26. But if this became too large, if it became a 27, that's not less than or equal to 26. So we can't do that. That's how I'm going to decide it. Now, what if the first digit started with a 3, or a 4 or a 5 or anything? That's never going to work, because if we're going to have some other second digit here, it's never going to be less than or equal to 26, right?
So I think one of the key differences here is the way that he's thinking and the way that I'm thinking is I'm thinking about creating the tree first and then looping through the list and mapping the string to the tree. And he's thinking about creating the tree as you go through the list. So the logic I was thinking is more like having from 1 to 9 on this level, and then on the other level we have from 1 branching off from 1 and from 2 the available decimals at the end. But he's talking about starting from the beginning of the decision, from the beginning of the string, and then moving according to the numbers based on the logic of every 2. So it's either going to be 1 or 2 digits that you take, and that's how you branch and increase the tree. And I'm thinking more about creating all the possible combinations of numbers. So that's the key difference, I think, and the way that he approaches and I'm approaching, because this is not intuitive to me, but it makes a lot more sense if you think about it, because you're only gonna have 2 decisions at any given moment in the string. So it makes sense to create the tree as you loop through the string, and then whatever logic you're gonna put inside of the loop of the if-else statements is gonna be based on the constraints of the problem.
Won't be. So we're only going to have 2 decisions, right? We're only going to have 2 branches if our first digit is a 1 or if it is a 2. So this is kind of the brute force approach that I'm showing you, but it might not be super efficient because we could have 2 decisions at every single position. Then our time complexity would be something like 2 to the power of n, where n is the length of the input string. So how can we kind of do a little bit better? Well, notice the subproblem that we're doing. For example, when we take just 1 by itself and consider, okay, this is just going to be one way that we decode it, then we're asking, okay, how many different ways can we decode the remaining of the string, right? That's the subproblem over here. We're asking how many different ways can we decode 21. When we take the first 2 characters, 12, then we're asking how many different ways can we decode the string 1, right? So that's kind of how the subproblem is going to work. The subproblem is just going to be some portion of the string, for example, starting from here all the way to the end of the string, how many ways can we decode this, or how many ways can we decode this, or how many ways can we decode the entire thing, right? To be able to solve this problem, how many ways can we decode this, we have to solve the subproblem, how many ways can we decode everything except the beginning. And so basically, how many different ways can we cache it? Well, we're gonna have some index I, which could either be here, or it could be here, or it could be here. It's just gonna designate starting from here and taking the remaining portion of the string, how many ways can we decode it. So basically, the dimension of our cache is gonna be n, right? So that's also gonna be the time complexity, because every time we get to a position I, at most we have 2 different decisions to make, right? So that's gonna be an O of 1 operation making those 2 decisions. It's not like we're gonna have to run through a loop or anything like that. We're not gonna have any loops, and you'll see that when I write out the code. If this is the size of our cache, this is also gonna be the size of our time complexity, and this is also gonna be the size of our memory. This is because it's the size of the cache. Now, just so you know, I think this problem actually can be solved when we write out the actual dynamic programming solution, not using a cache, not doing it recursively, but actual dynamic programming. It can be solved with O of 1 memory, because one thing you might notice, okay, when we want to know how many ways can we decode this entire string, well, when we're at a pointer I, we can either take this character by itself, in which case then we're going to shift I by 1 over here and ask, what's the result of this subproblem, or if we take the first 2 characters, 12, then we're going to ask, okay, what's the result of this subproblem, right? So we're either going to, basically, to set dp of I, we're either going to ask a dp of I plus 1 or I plus 2, right? Those are the only ones that we would need to look at, right? To compute a value like this, we only need to at most look at 2 different positions that come after it. So, when we have our dp cache, we actually don't need a full array to solve this problem. We could do it with just two variables, similar to like a house robber problem approach to dynamic programming, or like a Fibonacci sequence problem, right? But with that being said, I think we're ready to get into the code now. But before I do, let me just give you a very quick word from our sponsor for today. If you want to get hired at top tech companies like Google, Facebook, and Amazon, then now let's write out the code. So the first way I'm going to show you the solution is basically the recursive.
So I think a key distinction here in the way that he's thinking is he's thinking from the frame of mind of I have to give as an answer the decision tree, the possibility of the decision tree. So the way he's approaching is how can I create the decision tree based on the constraints of the problem, which is going to be the combinations. So the tree itself are the combinations, all the possible combinations. And I was thinking from the perspective of how can I create how can I create a tree with all possible combinations and then solve from that the problem. So my thinking is more because I think that the reason why I think this way is because if I'm gonna use the algorithm a bunch of times, it makes more sense to me to have all the possibilities into one thing and then search whatever I want to search in that structure that I have. But I think it makes more sense and is not that intuitive to me to create the algorithm from the perspective of the problem itself and not the structure. Yeah, so I'll have to think more about that, but I think there's a key distinction there that I can change in the way that I'm thinking, so these problems become easier to solve.
caching solution, the O of n time and memory solution. So we're going to initialize our cache. We are going to put a single value in here. Basically, the entire length of the string is going to map to 1, because if we get an empty string, we want to return 1 in that case. That's just kind of our good base case, right? And then we're ready to write out the recursive function. I'm just going to call it DFS, pass in a single variable I. Basically, I is the position that we're at in our string S. Now, one base case is if I is in our DP, meaning either it's already been cached or I is the last position in the string, in which case that's our base case, right? And then we would just return DP of I. So that's, our good base case. It's either been
I think I understand now. The purpose of the dynamic programming is to create an algorithm that creates the tree of possibilities. And I'm thinking about an algorithm that searches the tree. And I think that's the key distinction that's why it's a different branch. That's why you have trees as a data structure and then dynamic programming as a separate thing. Because even though they are the same thing, dynamic programming has a purpose of creating the tree of possibilities, and the tree data structure has a goal of searching the tree that already exists. And that's the main distinction, I think.
cache, or it's just the end of the string. Our bad base case is going to be if it's not the
And that's the reason why I'm confusing both of them, because I'm trying to solve dynamic programming problems from the paradigm of the tree problems, because I thought it was pretty much the same thing.
end of the string, then we have to check what character it is. If the character is starting with 0, right? If the string is starting with 0, then it's invalid, right? There's no ways to decode a string that starts with 0. So then we have to return 0. So that's like our bad base case. So these are the two main base cases that we have. But remember, if it's not 0, that means it's between 1 through 9, in which case we know we can take this value as a single digit, right? So then the subproblem becomes DFS of I plus 1, right? So that's what the result is going to be. We're just going to call DFS on I plus 1 because we took the character at I as a single digit, right? But we know that there's some cases where we can also call I plus 2. Now, what's a good way that we can write out that case? Well, first, this is one of the ways you can do it. I'm sure there are better ways, but basically if I plus 1 is less than the length of the string, basically if we do have a second character that comes after the current one, right? Because we're looking for a double digit character. So if I plus 1 is in bounds and either the character S of I starts with a 1, right? S of I is a 1 because if it starts with a 1 and there is a second digit, that means that definitely we can take a double digit value, right? Because anything between 10 all the way to 19 is a double digit value, right? So as long as it starts with 1, we know we can make a double digit value. Or the other case is basically, I'm trying to figure out a good way to format this in a readable way, but basically, or if S of I is equal to 2, right? It starts with a 2, but if it does start with a 2, then the second digit, right? S of I plus 1 must be between 0 and 6, right? How can we check that? In Python, at least we can check, okay, if this character happens to be in this substring 1, 2, 3, 4, 5, 6, right? Basically, we're saying is that second digit any value between 0 through 6. At least this is a clean-ish way to write it. So I encourage you to reread this condition if you don't fully understand it, but it's basically what I mentioned in the drawing explanation. We're basically checking if this double digit value is between 10 to 26, so then we can actually take it as a double digit value. If we can do that, then to our result, we're going to add DFS of I plus 2, right? It makes sense we're doing I plus 2 because
And that's another pattern that I've seen on tree structures as well. So here he's applying this method, which is pretty much you have recursive calls and then you put the flow of search in the recursive call based on the conditions you have of the problem, the restrictions. And yeah, so he's applying this tree stuff here, but the fundamental part of the problem is creating the tree.
This is a double digit value. The subproblem becomes I plus 2. And then once we're done with that, we can just go ahead and return the result. But before we do, don't forget to cache it. So dp of I is going to be equal to result. We're caching it, and then we're going to return the result. And then, when we actually want to return the result in the outer function, we can just return DFS of 0 because we want to know how many ways can we decode the string starting at index 0. And I ran it, and as you can see, it works and it's pretty efficient. Let me just copy and paste the actual dynamic programming solution. I don't want to waste too much time to write it out because it is very similar. And I think if you can come up with the recursive approach, the logic for the dynamic programming solution is also pretty simple. We have the exact same cache. The only thing is we're doing this bottom up. So we're starting at the end of the string, iterating in reverse order. We have the same base cases. Basically, if S of I starts with 0, then the DP is going to be 0, right? And basically, this is the same as these two lines of code where we just return 0. Else, meaning, that means it's a digit between 1 through 9. Then we can call dp of I plus 1. That's the same as when down here when we call DFS of I plus 1. Now this bottom part is the exact same as the if statement we had down below, right? You can see the logic is the exact same. The condition is the exact same. Only difference is here we're saying dp of I plus 2 is added. Down here, instead of using dp of I plus 2, we actually called the recursive function DFS. So the logic is definitely pretty similar. And in this solution, at least the memory is O of n. But I do think that you can, instead of having an entire cache or array or whatever you're using, you can just have 2 variables. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
It's gonna take me some time to really understand how to solve these problems, or until I'm able to solve them in less than 20 minutes. We're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Okay, so I have an integer array of coins representing coins of different denominations and an integer amount representing the total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of coins, return -1. You may assume that you have an infinite number of each kind of coin. So again, I have to think from the standpoint of the decision trees. Creating the possibility of decision trees. So for each coin that I choose, that I select, so pretty much there's no restriction, I think. All I have to do is figure out all the possibilities of combinations in the to create that. I guess I can use Ether2's combinations as well, or product, to figure out this out, but fewest number of coins make up that amount. And that's the only restriction. So it has to be the shortest path, pretty much. I'm probably gonna memorize here something. So what I'm thinking about is decreasing. Obviously, I need to decrease the amount of total each time that I search. But how can I create all the possible answers? And then how can I measure the paths, the amount of steps that I take? So maybe I can loop through the original one and then call the function. And the function searches for all the possibilities. I think that's a better, at least it's easier in my mind. We're calling coins, I call DFS with coin. And then from each coin, I'm gonna select RAM, which is gonna be remaining. There's gonna be coins. Yeah, but I can't, as I pass C here. Oh, but that's not, it doesn't work. I could just do coins pops here. Yeah, but then I can't call recursively. That's the issue. Oh, actually, I don't need to modify the original one because I can reuse the same value. But then how do I find... So I'm thinking about trying to find all the possible paths until I reach the target from this depth first search for each value in the beginning list. The only thing that I'm not sure is how I'm gonna know the shortest one. So maybe I can have a step. And how do I test all the possible combinations? So I'm gonna have an object here as well. Is that just another pattern I see a lot. So if C not in visited C equals C. Here I'm gonna call DFS. Yeah, I can't really do in a loop, that's the issue. I can't mix both, I think. I either need to figure out a way to do it with the for loop or with the for search. Because so I'm gonna move through the... Or maybe I just pass for I in range. That's probably better. In range coins, length of coins. And then if coins, see, nothing visited. And then here I call with C plus 1. But then I don't need the first one. Or I can have two different. And then I scratch this thing here. Just do the... So it's pretty much the same thing. I'm just recursively going through. If C greater than recursive length of coins, turn. So the only thing that I can think about is how I'm gonna know which one is the shortest. Because I need to select from the basket each time. I need to do, because obviously I'm gonna do this, coins C here. Or amounts 0. And I can't go less than 0, obviously. Damn, this is hard. I have this structure, it's just difficult to think about. Again, how to construct the path. Because I can't go from the end of the loop if the amount is not 0. and there are no coins that can make the amount 0, I can't just remove the path that I just created from the recursion, because that would be an invalid path. So that's one problem, and the other problem is that even if I create all the paths, I don't know which one, how to choose the shortest one. So maybe I should have a minimum at some point. Yeah, I should have an accumulator of steps and a minimum, probably. So what I'm thinking about is another variable here outside, then I store the number of steps into that variable and then compare. So I make if total, or I can do in a dictionary as well. So I check to see what was the previous steps. And if the current one is bigger, then I don't. I just return the other one. And the thing is that this one is not gonna give me as well all the possibilities because I'm just going from left to right. So it doesn't work. I need something that branches from the same list each time. Because each input of the first one has the same amount of outcomes from the first list. So I know that is probably a recursive call, but I just don't know how to structure. Again, it's the same issue that I had on the previous ones. Because I know from 1 it's gonna branch off into 1 to 5, and then so on and so forth until it reaches the 11. The amount, so I know one of the conditions I need to have is to check if the value, if maybe I should have a total here equal to, then I increase the total instead of checking for the amount. But I think it's the same thing at the end of the day. Oh, the difference is that with the total I can make it equal to 0, and if I change the amount, then I can't go from all the possibilities. So maybe I need a different value here. Yeah, but at the bottom line, I need a condition that checks to see if this restriction was reached, which is the total sum is equal to the amount or greater, and then return. That's one thing. The other thing I need to think about how I can structure this into this dictionary here, all the paths, the possibilities, which I kind of forgot from the previous one, how he did it. Maybe I can create 3 different if statements here and decrease each time, but that doesn't make any sense because the branching off of the decision tree has to be made on the decision, on the recursive call here, I think. So I need to put an argument here that when I call it, I can change the space of possibilities, the navigation inside of the tree. And I don't remember how to associate this with this one. Maybe I should look at the solution of the previous one.
Hey everyone,
Try to
welcome
remember
back
how I did it.
to cache it. So same base cases basically.
So if I in the P return DPI for search. Let me go in the other one.
Result, we're gonna add DFS of I plus 2, right? It makes sense we're doing I plus 2 because this is a double digit value. The subproblem becomes I plus 2. And then once we're done with that, we can just go ahead and return the result. But before we do, don't forget to cache it. So dp of I is going to be equal to result. We're caching it, and then we're going to return the result. And then when we actually want to return the result in the outer function, we can just return DFS of 0 because we want to know how many ways can we decode the string starting at index 0. And
So he's passing the index, and then he's checking if the index exists on the memorization here. If it is, he returns that. If it's 0, returns 0. Oh, so it's on the return statement that I should be branching off. And then he calls a plus 2 here. DPI equals Ross. So I think this returns on the rest here is going to return all the possibilities from the recursion call. Yeah, that's the difference, is that my situation, the only condition is at the end. So maybe it's more simple than that. So in the cache, you should have all the possibilities of the list, the initial list, and then I should go, yeah, I think that's how we do it. If I had more time, I think I could do it actually. Because it's pretty much the same thing, but the only difference is instead of doing the cache like this, I would put the initial list with all the possibilities here, and then I would call recursive, store the value in the variable. Yeah, but then the only condition here is, the problem is this one, because the lookup, I would have to, well, actually I can look up the 3 possibilities each time, and you store on this value. And then at the end I return the thing. Yeah, but then I would have to figure out how to get the, because here he's trying to get all the possible combinations. So I don't know how would I make it to get the shortest combination. That's the difference. So let's look at the solution. I think I'm gonna stop after this one.
Hey
Take a break.
everyone, welcome back, and let's write
Come
some
back
more
later.
LeetCode today. Today, let's solve another classic dynamic programming problem, coin change. And we get a pretty simple description. So we're given a list of coins of different values, and we're also given a total amount of money that we want to sum up to. But we want to use the fewest number of coins possible to make up or to sum up to that amount. And it's possible that that amount of money cannot be made up with any combination of the coins that we have, and then we want to return -1 if that's the case. And luckily for us, we're actually given an infinite number of each coin. So in the first example, we have coins of value 1, 2, and 5, and we have infinite quantities of these coins. The amount that we want to sum up to is 11, and basically, just look at this. What's the fewest number of coins we could do? Well, of course, we want to use a 5 because it's the biggest one. We can use another 5, and then we just need a 1 left if we want to sum up to 11. So in this case, you can see we only needed 3 coins. This is the fewest number of coins we needed, so we can return 3. In the second example, we have
Oh, that's another thing, obvious thing that I forgot. You should obviously try to use the highest values first.
Point of value 2, but we want to sum up to 3. We can try 2 plus 2, but we know that's 4, so we went over 3, so there's no way to possibly sum up to 3, so we return -1. There's no possible solution. So your first idea might be, can we just be greedy? Is the problem that easy? Can we just be greedy? And let's look at this example. So let's say these are our coins 1, 3, 4, 5, and we want to sum up to 7. So when I say greedy, I mean, okay, we want to sum up to 7. Let's just start at the biggest coin we have. So let's start at 5. So now let's look at the biggest coin again, 5. If we add a 5 here, we know we're going over the total amount 7, right? So we don't add another 5. Well, let's look at the 4. Well, we know 5 plus 4 is also going to be more than 7. 5 plus 3 is going to be more than 7. Okay, but we found a 1. Luckily, we have a 1. So let's add 1 to it. Now we're at 6. So let's add a second 1. Now we got to the sum 7. So we basically went down from the biggest, smallest coin values, right? That's what I mean when I say greedy. Let's pick the biggest one possible first. So notice that this took us 3 coin values, right? So our result in this case would be 3. But is that the minimum amount of coins? The answer is no, because, just looking at it, we can tell we got a 3 and we have a 4. 3 plus 4 is 7. That means the minimum amount of coins is actually 2. So this is a counter example. We cannot be greedy if we want to solve it. So the next thing you might try is like a brute force solution, right? So to do the brute force solution, we need to implement some kind of depth first search or backtracking solution, right? So let's look at the same example, 1, 3, 4, 5, and amount sum to 7. So what would a backtracking solution even look like for this problem? Well, it's going to be brute force, right? So we have 4 coin values. So that means in our decision tree, we have 4 possible choices. We can choose a 1, we can choose a 3, we can choose a 4, or we can choose a 5. In this case, the remaining amount would be 6 because 7 minus 1 is 6. In this case, the remaining amount that we have to compute would be 4 because we're taking 7 minus 3, which is the coin that we chose. So we get 4 as the remaining amount, right? In this case, we would have a 3, and in this case, we would have a remaining amount of 2. So since none of these are 0, once we get to 0, we know that we've computed the total amount that we want. But right now, we have to continue going, right? We have to continue doing the brute force approach. Let's start at this side right now. So we still have adding values to it, the minimum amount of coins, but we found an algorithm that at least tells us a possible solution. We will have a remaining amount of path because we already know if we have an amount 1, it takes only a single coin for us to be able to reduce it to the amount 0, which is what we're looking for. So since this subproblem repeats, I don't have to compute it. I can just borrow from over here. So in that case, we see the same thing happened though. We use a coin 1 and we get 0, and we see that, okay, it took 3 coins for us to get to 0, right? We took a 1, a 5, and another 1 from over here. So basically we got the same thing that happened over here, just in a different order. And just to make this a little less messy, I'm just going to tell you that none of these are going to lead us to the optimal solution. So now let's look at this case. We have a remaining amount of 4. How many coins does it take for us to get an amount 4? I'll just tell you from here, if we have like a cache top-down memoization because we're doing it recursively, but you can actually solve this with a true dynamic programming solution, which is bottom up. And it means exactly what it says. So bottom up, basically, instead of solving the original problem where the amount is 7, we solve it in reverse order. We start at the smallest one, which is 0, right? This is 0 over here. So we want to know what's the minimum number of coins. We can call it dp of 0. So for amount equals 0, what's the minimum number of coins for us to sum to 0? Well, we know it just takes 0 coins, right? What about if we want to know what's the minimum number of coins for summing to 1? Well, we can look at our coins. We got a 1, a 3, a 4, and a 5. These will all cause it to be greater than 1, but we just want a 1, so we can take just this, meaning it only takes us 1 coin to sum to 1. And then we can just repeat that process, right? So for a dp of 2, so we want how many coins does it take for us to sum to 2? Well, we got 4 coins, right? These 3 will cause it to be greater than 2, so we don't use those. But what about this one? Okay, we get a 1, so it takes 1 coin to sum to 1, but that's something we already knew. So if we want to compute dp of 2, we can take 1 plus dp of 1. Because we know these 3 coins are going to be too big, but we have a 1 over here, that's value 1, and we also know that that's not enough, right? 2 minus 1 still leaves us with a remaining amount of 1, but we just computed that up here. We know for us to get the minimum number of coins to get a value 1, it only takes 1 coin. So that means that if we want to get amount 2, it takes at least 2 coins. And let's say we repeat this process for all values, for all amounts from all the way, starting at 0 all the way to 7 over here. So I computed it from all the way from 0 to 6, but the last one we really want is amount equals 7. So let's compute that dp of 7. How do we get it? Well, we still kind of have to check every single coin. So what happens if we get coin 1? Then we take the result of 1, meaning that's how many coins we use, not the value 1, because we needed 1 coin with a value 1, and now we have a remaining amount of 6, right? dp of 6. So how many coins did it take for us to compute dp of 6? Well, we already computed that. It took 2, so we get 1 plus 2 equals 3. So that's one possible solution. But is it the minimal solution? Well, let's look at if we use the coin value 3 over here. Well, it takes us 1 coin, so we take 1 plus dp of 4, because that's the remaining amount we have to use if we take a coin value of 3. And luckily, we already computed dp of 4. It is 1. So then we get 1 plus 1 equals 2. And we know that this is the real result that we want. But even before we know that, we would repeat this process. So technically, if we do the bottom-up dynamic programming solution, we are going to repeat this for the remaining 2 coins. So for 4, we would get 1. So we'd have 1 plus dp of 3, because 7 minus 4 would leave us with a remaining amount of 3. And in that case, we know dp of 3 is 1. So we would have the total of 2 again. So we see that there are actually 2 solutions. And we know we have one last coin that we technically have to check, coin 5. So we'd use 1 coin for value 5. And then the remaining amount we'd want to compute is dp of 2. And we know that dp of 2 is value 2. So this would result in a 3, which is not what we want, right? So from these 4 values that we computed, we want to take the minimum, which we know is 2, so we can return 2 in this case. So that took us forever, but luckily the code is a lot shorter. So just like we showed, I'm going to have a dp array, and I'm going to initialize this to be length of amount plus 1, because we are going from 0 all the way to amount. And the default value I'm going to give each element in this array is amount plus 1, or you can do like infinity or whatever the max int is, like math.max integer or whatever in your language, but amount plus 1 is basically a max value anyway. And we know that the base case for this is the dp of 0, meaning if we want to compute amount 0, that it only takes 0 coins. And now we're going to start computing every value in dp, so for every amount a in range, and we're going to do this in reverse order, or rather bottom up. So we're going to go from 1 all the way to the amount. And we technically are still doing it in a brute force way, so we are going to go through every coin. So for coin in our list of coins, so we're trying to compute this a amount. So we're going to take a and subtract the current coin that we're looking at. If this is non-negative, so if it's greater than or equal to 0, that means we can kind of continue searching, right? So this means we possibly found a solution for our dp. So for this amount a, we're going to set it to the minimum of itself and 1 plus dp of a minus c. So this 1 comes from this current coin that we're using, c, and dp of a minus c comes from, for example, let's say our coin value was 4 and our amount that we're trying to compute, a, is 7. Basically, we're saying dp of 7 is equal to 1 plus dp of 3, because 7 minus 4 is 3. So we're saying that this is a possible solution. And actually, that's the only thing that we have to do. This is basically it. This is like what's called the recurrence relation. And so now the only thing we have to do is return what we're looking for. So dp of amount. So this is what we have to return. But we remember one last edge case. If we could not compute the amount, meaning if, so we can only return this if the value that's stored is not the default value. So if it's not equal to amount plus 1, right, which was the default value that we gave it. So we'll return this if it's not the default value. Otherwise, we're going to have to return -1, meaning we could not compute this amount with the given coins. So this solution does work, and even though it's pretty efficient, the time complexity is actually big O, the amount that we're given, multiplied the number of coins that we're given. And the memory complexity is big O amount, because we see we have a dp array that we're having a potential value for every single.
Yeah, to be honest, I still don't get it. I think it's gonna make this, the size of this equals to amount plus 1 times amount plus 1, makes the initial value equals 0. But I still don't understand the logic on how he thought about this. It's really confusing. So he's looping through the amount and first C coins. And through the coins, subtracting the amount. And then, okay, so he's making the value of the spots. Yeah, I think I understand the solution, but I don't, it really doesn't help in when you're trying to understand how to come up with a solution like this. Because although this is similar from the previous one, it's completely different as well. But I guess I'm starting to understand the fundamental principles behind these problems. And what that first search is as well. Just pretty much is either going to be, so bottom up is this way, it seems like. And then top down is the recursive way, where you put the conditions and you flow from there. But I think all of them involve looping through something, and then out of that list or linear structure, you create a tree. And the tree is either going to be bottom up or top down. And I think that's the main logic. And when it comes to dynamic programming, you're usually going to have something to memorize some aspects of the tree so it's more efficient. So I'm gonna stop here for now, and I'm gonna come back today soon to keep going on this list. So see you then.